Hello guys, welcome to the CHM 61004 Organic Chem, okay, Chapter 1. Okay, so today we are going to talk about atoms, the building block of matters. Alright, before we start this chapter, let's look at the overall journey throughout the whole organic chemistry. So this organic chemistry, we have altogether 7 chapters. You can see from here, 1, 2, 3, 4, 5, 6, 7. Okay, the first 2 chapters, atomics, the building blocks of matters, and the forces between the particles. These 2 are fundamental, very important. We talk from the very basic and fundamental of the atoms and forces, what are the molecules made of, what are the compounds made of, okay, which is basically the atoms, the building blocks. And then in second chapter, we are going to talk about how these atoms actually come together, okay, what are the forces that make them come together to form what we call compounds or molecules. So this is very important because after that, we're going to concentrate more on the organic chemistry, and which is chapter 3, 4, 5, and 6. We're going to highly look at the functional groups, right? The functional groups, hydrocarbons, organic reaction mechanisms, geochemistry, and the different types of functional groups. Then all these 1 to 6, all this knowledge you gain from 1 to 6 is going to be utilized to talk about chapter 7. Chapter 7 is basically to talk about the carbohydrates, lipids, amino acids, and protein, which is basically the fundamental and building block of food components. The food components will be built mainly of these 3 things: the carbohydrates, lipids, amino acids, and proteins. Alright, so please make sure you pay attention, have a very strong foundation of number 1 and 2. Okay, then we can concentrate more on 3, 4, 5, 6. And then lastly, this one will tie down all together and will be very useful for your food product development. Okay, the learning objective for this chapter is to able to understand the structure and composition of atoms found in the periodic table elements, able to calculate the atomic weights and molar mass of atoms found in the periodic table elements. This is very important. Alright, when you are in the food industry, you surely will need to calculate, because it can be reactions, it can be how much ingredients you need to use, okay, technical ingredients I'm talking about, okay, and how much to react and so forth. This calculation is very important. Third is to understand the configuration of electrons around the nucleus of atoms found in the periodic table elements. These electrons surrounding the nucleus, this is the one that helps to look at how they form, okay, whether they are forming molecules or compounds, okay, how they actually form. We discuss more on this later on, yeah. Understand how the periodic table elements are arranged so that information can be easily obtained. Okay, so this is a very basic. This one basically number 4 teach you how to look at the periodic table elements so they can quickly obtain information from the table. Okay. Okay, let's look at the week 1 part 1. Okay, so week 1 part 1 we're going to concentrate on these 3 areas, which is this lesson's main topics, the atomic structure and compositions. Very basic. This is very basic. Atoms composition of different elements, and then looking at how you calculate the atomic weights and molar mass. Okay, let's look at the first one, atomic structure and compositions. These are some of the just a terminology, okay, to differentiate. When we talk about elements is a chemical which include only one kind of atoms. But when you talk about compounds, it will be more than one kind of atoms stay together. Okay. So what are the building blocks of all these elements and compounds? It can be anything. The compounds, the elements, the basic building block is actually atoms. Okay, the things you look, the things you see now, everything is made of atoms. Okay, so let's look at the atoms. What is it composed of? Because the most basic unit, atoms is basically the most basic unit, and it's made of these three things. You have a proton, okay, neutrons, and electrons. So the proton and neutrons is they form what we call the core, alright, and the electron is surrounding it at the outside. Okay, so every atoms we have this basic structure: a proton and neutron at the middle, and the electron at the outer shell there. Okay, so these three particles of the atoms, right, they are differ in these three things. Okay, the protons, neutrons, and electrons, they are different in these three things. The charge, okay, whether is it positive, whether is it negative, okay, whether there's no charge, mass, whether is it heavy or whether they are light, and space occupancy is basically the area, okay, whether is it a small space or it will occupy a larger space, okay, a small space or they are larger space. Okay, let's look at this. These are some of the very basic. We just are looking at the components of the atoms. Protons is always positive. Okay, protons positive. We actually mark it as +1, and then the neutrons. As you can see, neutrons neutral, neutron neutral, no charge. Electrons basically is negative charge. Okay, we have a -1. Okay. So proton have positive charge, neutron is neutral, and electrons has a negative charge. This is the other difference is basically in mass. Alright, the mass, proton and neutron, they have similar mass. Okay, 1.67 times 10 to the power -424. And the electrons is very light, a lot lighter than the proton neutron. You can see is -28, which means that in front there are a few more zeros. Okay, so it's very, very light. So proton, neutrons, which is the core, heavier, electrons is outside, okay, which occupy much more space. The relative mass is basically is just for easier reference, because 1.67 times 10 to the power of -24 is quite difficult to actually write it down. You can use what we call the relative mass, okay, U, okay, so 1U, 1U, 1 over 1836U, okay. And the third difference, right, is basically the space occupancy. Proton and neutron is a lot heavier. That's why it makes sense that it actually occupy a smaller space, which is at the core there. Whereas the electrons, okay, electron is much more smaller, okay. And what happens is that it will move around, okay, the proton and neutron, okay. And because of the lighter weight, it can do so, and it will occupy outside of the neutron and proton. So you can see from here, proton and neutron at the core there, you can see the electrons are surrounding outside. Alright, so this one is basically the very basic information, okay, basic but fundamental information about the atoms. We can all these theories are basically backed by the evidence. Those like for example in this case, right, is the scanning tunneling microscope, okay, and is not using the is using a probe to actually scan the surface, okay. So you can see the probe scanning the surface of any sample, And if you sense the sample, and this is basically a surface of a palladium, okay, like the commonly use it to make the wedding rings, okay. So you can see that when they scan through, they can see a little bump over here. Each of these is one atom, okay. Each and single of this bump is actually one atom. Okay, the second one is we will look at atomic composition of different elements. The number one that we have just gone through is basically all this applies to different elements. Alright. By the way, when we're looking at elements, you can look at these periodic table elements. I just quickly come over here. Okay, if you can see over here. So you can see from here, we got a lot of different elements. This is what we call the periodic table elements. We got, in this world, we have discovered a lot of elements, okay. We got hydrogen, lithium, berylliums, okay. We got carbon, we got nitrogen. So these are some of the common ones. Oxygens, alright. Sodium, potassiums, okay, calciums, okay. So all these are different elements, sorry. All these are different elements. They are made of the same component, which is atoms, and the atoms, they compose of the proton, neutrons, and electrons. The only difference between all these, right, is that they have a different number of these components, okay. So which is in this section, I'm going to talk more about it. Okay, just move over the screen. Okay, let's look at this atomic composition of different elements. Alright, so you can see from here. Alright, so what's the difference? How do you differentiate between these elements? Okay, I go back one slide. How do you differentiate? You got hydrogen, okay, lithium, sodium, and so forth. How do you differentiate all this? There will be one component of the atoms that differentiate this, okay, and the answer is basically the number of proton, okay. If you look at each of these, they have distinct number of proton. Like for example, if you look back to the periodic table elements, hydrogen have one proton, okay. Regardless of what, whenever you got one proton in the element, it will be hydrogen. It will be hydrogen, okay. And if you look at the oxygen, okay, oxygen, we have the number of proton is 8. So regardless of what, if it have proton number amount of proton which is 8, it will be oxygen, okay. So how do you look at the whether is it 8 or what is the number of proton? You can refer back to these periodic table elements. I have included in your handout, okay, so you can look at it. You can download the handout and have a look after the class, okay, or you can open it now, okay, pause the video and open it now, and you can see over here the periodic table elements. Okay, just over here, let me just drag over here. Okay, so you have a look at this. If you open up your periodic table elements, in the top part you'll see one of the description of the periodic table elements. You can see over here the top left hand side. This is what we call atomic number. This actually represent the number of proton. How many protons are there? Okay, the proton element. The proton components of the atom. Alright, so you can see from here, if you see when you written 1 means 1 proton, okay, 3 means 3 proton, and so forth. right? So the atomic number or number of protons, okay, so these are interchangeable, alright? If it's 1 is hydrogen, if it's 3 is lithium, and so forth, okay? Okay, let's try this one here. Please determine the atomic number for the following elements based on the periodic table of elements. So you can pause the video, take out the periodic table of elements and try to do this. Okay, look at the top left hand corner of the number, what we call the atomic number. Alright, so this is the answer. If it's hydrogen is 1, carbon is 6, oxygen is 8, okay, and the nitrogen is 7. Okay, sorry, over here it should be 8. Okay, alright, so it's 1, 6, 8, and 7. Alright, so you can do it. Okay, you can do this. Alright, so again, if it's 1 means there's only 1 in the element is only 1 proton in there in the middle. Okay, if it's 6, there are 6 protons inside the elements. Okay, if it's for oxygens in the middle, okay, in the middle there are 8 protons, and nitrogen there are 7 protons in there. Okay. Okay, this is using symbol. This is how you describe the atomic numbers using symbol. So what you do is that you put the X is anything. Okay, it can be hydrogen, it can be carbon, and so forth. And the atomic number you put at the lower left hand corner over here. Okay, for example, these are some of the practice exercise. You can do it. Okay, let's try this first. Alright. Here, if it's hydrogen, you put H, okay. If it's Z, how many atomic number, or the number of proton, if it's 1, you put 1, okay, H, 1. Okay, let's try. Okay, so this is the answer, H1 for carbon is 6, here, again, this mistake is 8, okay, nitrogen is 7. Okay, and 7. This is how you represent it. So in the exam, it asks you to use symbol to describe the atomic number. So this is how we do it. Alright. How many electrons are there in an element? Okay. This is a bit tricky questions. Okay. Normally, if we talk about the elements in the periodic table of elements, okay, we call it as this is what we call it, yeah. We call it as the electrically neutral elements. Electrically neutral, okay. Electrically neutral. Okay, let me just write down, yeah. Neutral. Sorry. Okay, electrically neutral. So means that there's no net charge. So if just say you got 1 proton, then you got 1 electron. Okay, plus 1, negative 1. Okay, so the net charge is 0. Alright. Okay, so elements shown in the periodic table are electrically neutrals, no net charge. Okay, this is very important for you to differentiate. Yeah, no net charge. Okay, or electrically neutral doesn't mean that there's no charge. It's just that the net charge is 0. So they sort of like balance out. There's a positive and a negative, so they balance out. Okay, they balance out really. So the charge is still there. There's still positive and negative there. Just that their net charge is 0. Alright. So if you are looking at this, please determine the number of the electron for the following elements using the periodic table of elements. Okay, so this, if they have one proton, okay, basically they will have one electron. Okay, so it's hydrogen over here. If it's one proton, there will be one electron. Okay, let's try. Okay, so you look at this. Okay, there's an error here. Sorry about that. Okay, so you look at that. One electrons. Okay, there will be one electron because there's one proton, so there will be one electron. Here they have 6 protons, so they will have 6 electrons. 6 protons, 8 electrons, 7 protons, 7 electrons. Okay, this is a very tricky question now. Okay, so now we know that the number of protons is fixed. Okay, each element got one particular number of protons. Then we know that electrically neutral elements have equal number of the electrons. One proton means one electron. How about neutrons? Okay, how many neutrons would that be? Okay, atom of the same element contains same number of protons and same number of electrons, but they will have different number of neutrons. Okay, atoms containing same number of proton and electron but different number of neutron we call isotopes. Like for example, they will have isotopes of hydrogen. Okay, the hydrogen they will have it's fixed already. They have one proton, one electrons. Okay, but when they have different the neutrons, we call them isotopes. Like for example, over here, these are 3 what we call the isotope of hydrogens. Okay, all these are hydrogen. Okay, all these are hydrogen. Okay, because they have one proton. See, one proton. But they have one electron as well. You can see, but they have a different number of the neutrons. Like in here, there's no neutron. Here is 1. Here got 2. Okay, so all these are what we call the isotopes. Okay, so we can use represent using what we call the nucleon number. Okay, or A is the sum of the number of protons and the number of neutrons. Okay, so we put at the symbol. This is how we represent using the symbol. X is put the symbol of the element. Z is the number of the proton. A is basically the total number in combination of the proton and the neutron. Okay, so over here, the what we call the nucleon number. Okay, let's look back over here. Okay, so the nucleon number here, okay, is represented at this corner, so it's the total number of proton and neutron. In this case, the nucleon is 1 plus 0 is 1. Here is 1 plus 1 equal to 2. Here 1 plus 2 equal to 3. Okay, so this is how you express the 3 different isotopes of hydrogen element using symbol. Okay, please write the symbol for the atoms with this. Okay, 6 protons and 6 neutrons, 13 protons and 14 neutrons. If you're looking at this kind of question, first find out what is the symbol. Okay, what is the elements with 6 protons. Okay, once you have that ready, then you write the symbol. Okay, let me see, H or whatever. The bottom here is the number of protons, and the top part is the total number. In this case, is 12. Okay, let's try. Alright, so for 6 proton is carbon. You can see from here, corner here, 6. Okay, so it's carbon. So we put the number of proton here, 6. In this case, the nucleon number at the top here is 6 plus 6 equal to 12. Over here, 13 proton is aluminum. Okay, looking at periodic table element, the top left hand corner, 13. So you put the atomic number at the bottom here, and the nucleon is the combination of the 13 and 14. Add together is 27. Right, very easy. Okay, what are the nucleon numbers, atomic number, and isotopes number symbol for an atom that contains 7 proton and 8 neutron? Okay, this is very similar to same as just now the questions. Okay, so first find out what is 7 proton, what is the element. Okay, then after that you will add in the symbol and so forth. In this case, alright, let's try here. Okay, so the number is the element is nitrogen. Okay, 7 is nitrogen. Alright, the number atomic is 7 over, and up there is the nucleon number is the addition of 7 and 8, so is 15. Okay, so 15, 7, and the nitrogen here. Okay, the last section, which is one of the very crucial for the calculation. Okay, very crucial for any calculation of the chemistry. Okay. Okay, the third section is atomic weight and molar mass. Alright, just to recap here, the different masses of subatomic particles. Okay, we got proton, neutron, electrons. The most heavy one is proton and neutrons. The electron is much more lighter. Okay, the next section we'll learn about the mass of an atom. Basically, when you're looking at the mass of the atom, any of the atom, we're looking at the combination. You just add up all the masses of the proton. If you got one proton, then you add up what this mass plus this mass, okay, plus this mass. Alright. Okay, let's look at it here. Why do you need to calculate the mass of an atom? Okay, to calculate what we call the formula weights, and also to prepare solution with different concentration. Because when you want to measure something out, okay, you basically now in any of the things we do, a lot of times we actually quantify based on the mass. Okay, so there's no difference compared to this as well. Okay, the mass is how you quantify, because if you know how to calculate, okay, basically you can instead of guessing, basically you calculate the correct amount to react. Okay, for example, for reactions, okay, or to add into your recipes and so forth. Okay, so you will reduce, or maybe you will basically avoid wastage, because in the industry, every single components okay, for the production is very, very expensive. Okay, we are not talking about just a few grams, we're talking about tons. So we need to know how to calculate, right? So how to determine the mass of an atom? This is very interesting. For the mass of the atoms, you need to combine all these, the weight of these three components: the proton, the neutron, the electrons. Okay. But you will be asking me, okay, sir, I know that the every atoms, they got same number of proton, electron, but in the terms of isotopes, they have different number of neutrons, right? Okay, so for us, okay, what we do, right, is that we will average. Okay, like for example, how many percentage of the isotopes will be present if just say that we get a bundle. Okay, so we got a bundle of this, just say that is hydrogen. Okay, over here, how many percentage of the isotopes? Okay, like for example, the one with no neutron, how many percentage is that? Okay, those with one neutron, how many percentage, and so forth. Okay, And then after that, once we know the percentage of it, then we will average it out, and then this will be represent the mass of an atom. So very fortunately, in this earth, the percentage is fixed. Okay, so the amount of the percentage of the isotopes is fixed, so it's very fortunate. So now we just need to average it. Okay, the percentage is already known. Okay, so you do not need to find out. Okay, it's given even in the exam. If I ask you to calculate the average, the atomic weight of the element is given. Okay, so you just need to know how to calculate the average mass. Okay, so in this case, like for example in here, protium. Okay, the mass for this protium, okay, is the adding of this the weight of proton, one proton and one electron. So the total mass, there's no neutron here, yeah. So the total mass from these two is 1.0078 U. Okay, and deuterium, which contain one neutron, one protons and one electrons, will be 2.0141 U. Okay, so you have learned that already before. Okay, the weights of these neutron, the protons, yeah, is 1 U, and this one is 1/1873, yeah. And here is you add up the weight of one proton, two neutron and one electrons, so it will be 3.0160 U. Okay, let's look at the abundance here, what we call abundance in this earth here, in this earth. So 99.988% is going to be this. Okay, the protium, which is one electron, one proton. Over here, the deuterium is 0.011%, and this is, you can neglect, yeah, this one, no need to worry about it, it's very trace. So what you do, right, is that you will, how you calculate is that you multiply. So you 1.0078 U multiply 99.988. Okay, once you get this amount, then you multiply this, get 0.008 U. Okay, you can calculate and try that. And interestingly, okay, this is basically the amount. Okay, this is the number reported in your periodic table element. Okay, so this atomic weight is all given in the periodic table elements, but I want you to know how it was being calculated. Okay, how this one came about. So if I look over here, as you can see, okay, 1.008, okay, the unit number U. Alright, so this is the mass. Okay, how this came about is basically how I teach you calculate is the average of from this isotope plus this isotope, the average atomic weight. Alright. Okay, so you can find it from here. Hydrogen, for carbon is that. Okay, is a combination of 6 proton. Okay, they got 6 electrons, and maybe they got other isotopes as well, and so forth. So in the exam, I will give you all these numbers. So for example, I will give you the abundance. I give you this. Okay, what you need to do is to calculate the atomic weights. Okay, exam and tutorial question have these questions here. Okay, so these are some of the sample questions. So you can see chlorine has 2 stable isotopes because Cl35. Okay, 35 is a combination of the basically the nuclear number. Okay, then with a natural abundance of 75.77% and mass of this. So you given the calculation, you see, you got the mass, you got the abundance, and then you got this, you got the for this isotope. So all these are chlorine here. The only difference is the number of the neutrons. Okay, so this is one set, this is another set of data. Okay, so what you need to do now, right, is to calculate the atomic mass. So what you do is you have this, okay, the mass of this isotope Cl235 multiply 75.77%. Then after that you calculate the average mass of this, okay, Cl 37, okay, chlorine 37, and multiply that, and then you add up these two, you will get the atomic mass of chlorine. Okay, let's try. Okay, so we can see, so the atomic mass of chlorine is 35.45 U. Okay, so we can see from here, chlorine, let's see, okay, look at this, 35.453, okay, which is the same, okay, same now amount. Okay, which element has atoms that are nearest to being twice as massive as atoms of calcium? Okay, calcium is how big? Okay, calcium is 40.08. Okay, are nearest being twice as massive as the atoms of calcium. So what is the atoms that are nearly twice as massive? Okay, so 40, then if it's twice as massive, it will be 80. What is 80? Okay, so the nearest to 80 is what? The nearest to 80 is bromine. Okay, so we look at this. 80, 80. Oh, there you go. Okay, twice as big as calcium. Calcium is 40, right? So this is 80. 80, the nearest to 80 is 79.9. Cannot be this. Cannot be this. Okay, so the nearest one will be bromine, which is 79.904. Okay, to the nearest whole number, how many hydrogen atoms will be required to have a mass equal to the mass of a single carbon 12 atoms? Okay, hydrogen is how many? Hydrogen is 1. Okay, so carbon is 12. Okay, carbon is 12. Okay, so how many? So the answer will be 12. Yeah, you will take 12 hydrogen to equal the mass of a single carbon atoms. Okay, for us, U, the unit U, is what we call atomic weight. Okay, if U is what we call the atomic scale. So if we need to convert it to what we call the laboratory scale, which we can measure using based on gram. Alright. So when you convert from atomic weight to laboratory scale, which is the what we call molar mass, okay, they have the unit gram. Gram we can measure using our weighing scale. Our weighing scale don't have the unit U, so we can do a direct conversion. Whatever is in U, we can convert to what we call molar mass, grams per mole. Okay, I'm going to discuss more about what is mole. Alright. Okay, gram, you know what is gram already, right? Okay, per mole. Okay, let's look at what is mole, yeah. Mole is actually what we call the Avogadro's numbers, okay. 1 mole, okay, whenever we look at 1 mole, they will have 6.022 times 10 to the 23 particles, okay, that is fixed already. Okay, instead of saying this number of particles, we call it as a 1 mole. It's just look like, it's just like, we call it like 1 dozen. 1 dozen we always talk about is 12 eggs. Okay, so this is 6.022 times the 3 particles. That's a lot of particles in there, in the 1 mole. So whenever we talk about 1 mole, that is the amount of particles in there. So we can talk about 1 mole of hydrogen. They will have that much of hydrogen in there, in the 1 mole. 6.022 times 10 to the 23, okay? Hydrogen, so many hydrogen. 6.022 times 10 to the power 23. Okay? So what we can do, right, is you can do direct conversion, okay, from the atomic scale, okay, from the 12.01 U, okay, we can directly convert, okay, no need to do anything, we just direct convert from this into grams per mole. Okay, with this direct conversion, once we converted the unit to this, we can use it, can measure it using our lab, the weighing scale. Okay, let's calculate the molar mass for the following elements. Okay, so again, just recap. Okay, atomic weight is under U. You can find this. You can find this in the periodic table elements. Okay, you can direct convert that number into what we call molar mass, which is grams per mole. Okay, so oxygens, you can see we got how many? Okay, let's look at this. Sorry. Okay, oxygens. If you're looking at this, okay, oxygens. Okay, oxygens. We got 16. Okay, if it's 16, then is U. We can directly convert to 16 grams per mole. Okay, so it will be 16 U. Okay, then here calcium, we can direct looking at this. Calcium, okay, 40.08, okay, U. Okay, can direct convert to 40.08 grams per mole. Okay. Okay, if you have any questions, you can actually post in the Padlet. Okay, the Padlet link is in Times. Okay, you can ask the questions over there, and we'll answer. Okay, if there's no, if there's anything else, you can directly discuss over there. Okay, so I will stop here, and we will continue for our next lecture. Okay, which is the looking at for the next one, we'll be looking at this, okay, the deeper understanding of the electrons in atoms, and also the looking at the periodic table elements. Okay, thank you.